Okay, welcome back. So this is 9.9, and what we're trying to do is kind of back engineer um, these polynomial, or well, not polynomial, but power series representations for functions. Um, so what we desire is if you have a function that you know all of its derivatives for, we want to be able to rewrite it as a power series. So we want to this maybe it's an unknown function, maybe we don't know anything about it. We want to rewrite it as a sub n times x minus c to the n from n equals whatever to infinity. So I'll just say 0 to infinity, right? Okay, so the way we're going to connect the dots is to kind of do this backdoor thing using the geometric series. Okay, so representing functions by power series. So in I think it was, what session was that? It was like 9.6 or 9.7. Yeah, 9.7. We saw there seems to be a connection between these polynomial things and functions. We could, given a function, if it had enough derivatives, we could build a polynomial based on that function. That was called a Maclaurin polynomial or Taylor polynomial. Now we kind of want the same thing, but for one of these, where this is different from the polynomials because it goes to infinity, right? So somehow I want to be able to build these power series representations for functions. Okay? And in the end, you're going to see that the way we built the Maclaurin and Taylor polynomials, that's the way to go. That will give us the power series representations. But right now, it's kind of we're going to kind of backdoor the issue with the geometric series. Okay, so first the geometric power series. And what did that say? That said, and this was way back in 9.2, we had this form n equals 0 to infinity of ar to the n was equal to 1 all over 1 minus r when the absolute value of r was less than 1. Okay? What we're going to do is just rewrite this with x. And we'll see what we have is essentially a power series for the function 1 over 1 minus x. So letting r equal x, and also, well, just to make matters a little more simple, let's let a equal 1. We have this representation for this side over here. We could write 1 over 1 minus x is basically, I'm putting x in for r, is equal to this power series, x to the n from n equals 0 to infinity. That's just a power series where the a sub n's are 1, the center is 0, and that's it, right? So also then the radius of convergence for this case will be x less than 1. So great. It seems like we've kind of had the connection all along. We've just not made it explicit. In class, I think I probably introduced you, I sort of let the cat out of the bag already, but this is, a power series representation. The only problem is this representation isn't very useful because, if I was trying to figure out f of 1/2, I most certainly wouldn't plug it in over here, right? I wouldn't say, okay, that's equal to 1 plus 1/2 plus 1/4 plus 1/8 plus ... No, I would say this is equal to 1 all over 1 minus 1/2, which is equal to 2, right? You wouldn't use the power series representation, but the deal is we can use integration and differentiation to get to power series formula for something that is of use. Okay, in particular, because this thing looks so much like the derivative of the natural log, we'll be able to integrate this to get to that expression. So the big difference between this and the natural log is, well, the integral of 1 over just x is the natural log, right? this thing is not really what we want to work with. This isn't the thing we want to take the integral of if we're looking for a power series representation for the natural log. So the first kind of step is to play around with this power series and try to form new power series that are similar to it. Okay? And we do it via substitutions. You'll begin getting a flavor for it from creating the power series representation for sort of variable expressions based off of this idea. Okay, so here they're telling you C is 0, and we want the power series representation for 1 over 1 minus 3x. And it just comes down to a substitution into this form, right? So in our case, we let x be redefined as 3x, and note then the function 1 over 1 minus 3x is equal to the sum of 1. So a is 1 in this case, is this number up on top, and then r is just the 3x to the n from n equals 0 to infinity. Right? And that turns out to be our power series representation. That'll work for the absolute value of 3x less than 1. So our radius is going from negative 1/3 to 1/3. In general, I don't think there's any reason to look at endpoints in these cases, because if you remember the way we built the power series representation for, well, the way we built the geometric series formula, we kind of knew the endpoints were always going to be divergent. Okay. You could check, and putting in 1/3, you're going to get 1 to the n. Putting in negative 1/3, you get negative 1 to the n. Both are just geometric series types, right? They're divergent type geometric series. So it's clear, I think, at least in this case, that we don't need to check the endpoints. It will just behave like we expect it to at the endpoints, as it does in the same case for the geometric. Okay, so number 11. Let's look at this one. It's a little more. You have to be a little more clever this time, apparently. F of x is 3 all over 3x plus 4. And again, we're having this thing centered at 0. So the deal is to kind of get it, massage it algebraically into this form 1 all over, or a all over 1 minus x, right? So I'll start on this side, 3 all over 3x plus 4. I'm going to factor a 3 out of the denominator, so it'd be 3, or sorry, I want 1 minus something, right? So you could rewrite it as 4 plus 3x, and then factor the 4 out to get a 1 in this leading position, this pole position, so to speak. So 3 all over 4 times 1 plus 3/4 x. And then I can bring the 4 up into the numerator, so the a value at this point looks like 3/4. And downstairs I have 1. I need to write it minus something, so minus negative 3/4 x. Right? And so we're, from the original formula, we're basically setting r to equal negative 3/4 x, and then our a value will be 3/4. And then finally, our power series will be 3/4 times negative 3/4 x to the n from n equals 0 to infinity. Okay. All right, so I probably want you to rewrite it and make it look a little prettier. You can kind of say this is a power product to power rule. So I have 3/4 times negative 1 times 3/4 times x raised to the n, and then if you distribute the n to all three, you'd have negative 1 to the n, 3/4 to the n. Over here I have 3/4 to the 1, so that would be 3/4 to the n plus one of these factors, and then x to the n. So what do we have then? Negative 1 to the n times 3/4 to the n plus 1 times x to the n at the end of the day, n equals 0 to infinity. and it'll be convergent when the absolute value of -3/4 x is, again, less than 1. Okay? So in other words, taking the absolute value of -3/4 gives you 3/4, but we'll be left with x in between 4/3 and -4/3. Okay? And if we substituted, it's not maybe as clear if you substitute in here, but if you substitute it back into here, you're going to get, again, this 1 to the n or -1 to the n, so it'll be divergent at the endpoints. Again, kind of reasserting what I'm telling you is you don't have to check the endpoints for these. Let's look at yet another one. This time we'll take a non-centered, so these were all centered at 0. Let's look at one that's not centered at 0. And the algebra is just a little more tricky, but it's the same idea. So number 9, g of x equals 5 all over 2x minus 3, and c is -3. Okay. So at the end of the day, I need to have this form of something all over 1 minus x minus our c term, okay? In this case, 3. So let's go at it, right? So this is 5 all over 2x minus 3. Okay? I'm going to rewrite this x here as x. I want to center it at -3, so this should be x minus -3. It'll end up being x plus 3. So I want to rewrite x as x plus 3. So I have 5 all over -3 plus 2 times x plus 3. And what you've done is added in 6, right? So this is 2x plus 6, so I need to subtract 6. And then rewrite that. So I'll have 5 all over -9 plus 2 times x plus 3. Okay, I still need a 1 in this leading position, this pole position, so I can factor out a -9 from the denominator, and I can move that into the numerator, so -5/9 all over 1 minus 2 times x plus 3. Okay? Then what you're doing is letting r be 2 times x plus 3. Your a value will be -5/9, and you dump it into your power series, so you'd have -5/9 times 2 times x plus 3 to the n, which will be 2 to the n times x plus 3 to the n, and n is going from 0 to infinity. Okay, so at the end of the day, then this will converge where this thing, or rather the r value, the absolute value of that is less than 1, so it's convergent where the absolute value of 2 times x plus 3 is less than 1. In other words, where 2 times x plus 6 is less than 1 but greater than -1. In other words, 2x is less than, subtract 6 from both sides, you get -5, greater than, subtract 6, so that's -7. So divide by 2, so x is less than -5 halves, but greater than -7 halves. Okay. And then again, if you plug this into this formula, you see that's where you're getting, you're going to end up again, once you put it in there, you're going to end up with 1 or -1 raised to the nth power, which will be kind of the endpoints of divergence for the geometric series again, so you don't have to, even in this case, you won't have to check the endpoints. At least it seems that way. I would literally have to go back and rederive the geometric series to convince myself, which I think I've done it before, I just don't remember, to convince myself and convince you, I'm sure. But if you go back and see how the original formula for the geometric series is built, and you really iron out the details on this r thing, the absolute value of r needs to be less than 1 for convergence, you will see sort of the truth of it. Okay, at least I hope. Anyways, right. So we have all these ways of converting something that looks like 1 over 1 minus x into something which is probably going to be more useful to us. So, this is a bit silly to have a power series representation for this function because I can always just plug it in and have my answer. So this is kind of a powerless power approximation, a powerless power series in that way. So what? I want to take what I know and build upon it and try to see if I can get these other power series. And you could do this via substitutions and again integration and differentiation. Okay, so operations on power series, and we've kind of already shown you that basically we've been doing substitutions here. Let R equal this, let R equal that. So I think in the initial case, the simple operations, we kind of already covered that. Simple operations, where you can do these substitutions and you're kind of in the clear. Okay. The more non-simple substitutions are what's going to be of importance to us in building these new power series. So in particular, integration and differentiation again. So we saw in the last section that we could do this and it would conserve the radius of convergence, but not necessarily the endpoints of convergence. So anyways, this is the big deal. We want to be able to get a power series approximation for a natural log, right? So right now, the only power series representation for a known function we have is this stupid one, the 1 over 1 minus x. We want something a bit more than that, right? So in particular, number 21, we see this. F of x equals the ln of x plus 1. I want a power series representation for this guy. So how am I going to pull that off? Well, I know that this thing is equal to the integral from 0 to x of 1 all over t plus 1 dt. Right? Hopefully you can agree with that to some extent. Right? Basically, if you take the antiderivative of this, it'll be the natural log of the absolute value of x plus 1 evaluated from 0 to x. X is assumed, I assume we assume x is positive. I don't think the book is saying that, but I assume we assume that. And then we could rewrite this as ln of, sorry, this should be t, right? So the ln of x plus 1 when I substitute x in for t minus the ln of 1, which it will be a big 0. So ln of x plus 1, yeah, there's maybe an issue with the absolute values, but I bet in the book it says x is positive. Okay. So hopefully you can see that this has some truth to it. If you're not completely sold, at least it's kind of all right. I will agree with you, Dave. Right. So what? Well, this thing right here is basically just one of these things back here, right? We have all these clever tricks now. We can rewrite it as a power series. In other words, we can rewrite this as the integral, and we're letting r equal negative t and a equals 1 in our power series. We have the sum of a is 1 and then times negative t to the n, because this thing, literally is 1 all over 1 minus negative t. Okay? So this negative t is the r value that I want inside for my power series expression. So this is going from n equals 0 to infinity, dt, of course, from 0 to x. And then I need to integrate that thing. So in the beginning, you probably want to integrate term by term. But later on, you could just, once you get the hang of it, you just integrate the terms of the series, the expression for the terms of the series. But anyways, what do we have here? We have when n is 0, that'll be 1, and then when n is 1, that'll be negative t. So 1, sorry, I lost my 1, minus t plus t squared minus t cubed plus dot 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 dt. Oops, I already went and I expanded it. Now I have to integrate it. Okay, so integrating term by term, I get t minus t squared over 2 plus t cubed all over 3 minus t to the 4th over 4 plus dot, dot, dot. We're evaluating from 0 to x. Okay. And so I'm getting x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4 plus dot, dot, dot. And then in summation notation, you can go back and kind of just consider integrating the terms of the sequence. So negative t to the n plus 1 over n plus 1 is probably what we're going to get. Or in this case, negative x to the n plus 1 all over n plus 1, where n is going from 0 to infinity. And in particular, then, we need to probably separate out that negative part. So this would be negative 1 to the n plus 1. But that's not going to work for us. So there's kind of an issue there. But yeah, the issue is that when we work with this expression and we're integrating the expression, you would have had to have a chain rule on it, because it would be n times negative t to the n. Sorry, when I integrated it, it would be negative t to the n plus 1 over n plus 1, but then there would have been a u sub involved, so it would have been a negative floating about. So really, you want to separate way back here to negative 1 to the n times t to the n, and then that will kind of allow you to preserve the negative 1 to the n. Okay, so you don't end up doing something stupid like I just did. Okay, so it's just negative 1 to the n times x to the n plus 1 all over n plus 1. Okay, all right. So when you integrate, this guy will have the same interval of convergence as the geometric series, but you integrated it. So now you do have to check the endpoints. And in particular, then, it converges on the interval from negative 1 to 1, absolutely. And then you have to consider x equals negative 1, in which case you'll have negative 1 to the n times negative 1 to the n plus 1. So you'll have negative 1 to the n times negative 1 to the n plus 1 all over n plus 1. So this will equal a series of negative 1 to the n plus 1, which is negative 1 to the 2n plus 1 all over n plus 1. Negative 1 to the 2n is just positive 1, and then negative 1 to the 1, we just get negative 1 all over n plus 1. And this is basically just a negative times the harmonic series. So a negative times the harmonic series, is still going to be divergent. Okay. If you really want to, you can probably do some other test, but I think that's good enough, because that is obviously a harmonic, and then when you multiply a divergence series by a constant, it won't change whether or not it converges or diverges. Okay, okay, so at x equals 1, you'll have the series negative 1 to the n all over n plus 1, which is alternating series. This is the alternating harmonic series, but let's just go through the motions. The limit of 1 all over n plus 1 is 0. And then secondly, a sub n plus 1, 1 all over n plus 2 times the reciprocal of a sub n. Obviously, we have something smaller over something bigger, so that'll be less than 1. And so by the AS alternating series test, it converges. By AST, it converges. Okay, so hence this thing is convergent at that endpoint. Its IOC is going to go from negative 1 to 1. Oh, whoops, the other way around, right? It goes from negative 1 to 1. Sorry about that. Okay, and that's pretty much all of 9.9. And what we're seeing is hey, I can connect these functions to power series in some way. And in the next section answers the question of how can I create these power series without having to go through these obnoxious backdoor methods. Okay, thank you, bye.